Welcome to a lesson with Dr. Powell. Let's think about how good a Taylor series approximation is um, uh, in accuracy Y for a multivariable Taylor series. For instance, let's just take a look at the example that we had in the last video, e to the x plus y. Okay, so actually, we just borrow exactly what it was for single variable. Pretty much it's pretty exact. Now, let me remind you what it is for that. So you have m, and so m is like bounding the, it's the bound for a derivative. For the, let's see, for perhaps like the n plus first derivative, if you want your Taylor series to go up to degree n, so through degree n, then you look at, you bound the n plus first derivative, you have a bound that's, or a number that's bigger than it, it bounds it. And then you like take your distance away from your center, and you raise the n plus first power, you raise it over. So everything is an n plus one, or at least 1 degree more than where you ended here. And this actually bounds the rest of this. And this idea came from the derivation of kind of where this is looking at integrals, and clearly what's left is an integral, and you can keep on working that integral into pieces. But really, if you want to bound that integral, this really bounds it and give you something bigger. And so it gives you something bigger than the rest of the sum. It's kind of a nice feature. Anyhow, so how can we use this with multivariables? Well, remember, the multivariable Taylor series really comes from the single variable Taylor series with the chain rule and substitution and so forth. So really, and every term is really kind of equal to a term in the single variable type calculation. So if you want to bound the mth derivative, and let's suppose that, and also this bound is also true just on an interval. So let's work with that for a minute. Let's suppose that our interval is, let's suppose that we want x in absolute value to be less than 0.1 and y in absolute value to be less than 0.1. Okay. Away. All right. So that means that e, the biggest it can be, is e to the 0.2. So that's really a good value for m. So that could be our bound for m. Just let m be equal to that. And then this part is interesting. We're not going to have this anymore in the multivariable sense. So really, you have to be a little bit careful, because we want bounds on m actually serves as a bound for not just the n plus first derivative, but all the mixed partials of that, like fxxxxxx, where you go n plus 1 times, and fxy, just any mixture of x's and y's, n plus 1 times. So m is actually going to bound all those. But in our case, this was really nice, because all the mixed partials, no matter how far you go, are always the same thing, e to the x plus y. So that's an excellent choice here for an example, just because all these guys are the same. So really, we can use this as our m as bounding that. All right, and instead of this, what do we use? Well, it's kind of like we take all these terms and we like bound them all and then factor out the m out of all of them and just see what's left over. Simply what's left over ends up being ends up simply being like x minus our center, which is, well, in this case it will be 0, but just in general. So basically like this, x, and we can pick absolute value here, plus y minus b, and you raise it to the nth plus first power. Now, if you look at this and you look at the coefficients and what's obtained, it actually is the same thing that is appearing in the Taylor series expression, except it's just missing your fxx's and fy's and all that. But if you like bound those above by m and factor out the m, then you're good to go. It just simplifies things a lot. Okay, so this is kind of the deal. So instead of doing, so what we do is instead we replace x minus a to the n plus 1 and just replace it with this part right here. And then we still have over, and then we still take that and we put it over n plus 1, or sorry, n plus 1 factorial, right? So that's kind of the bound. So if we wanted to see how far off, so let's suppose this, okay, and let's suppose that we wanted to only use maybe up to degree 2. So use up to degree 2. That means that we have to do a third power here on everything, and we can still use as e to the point 2. And then here, in our particular case, what's the biggest? So, well, we're trying to evaluate x at 0.1, say. Let's just go all the way to the end, 0.1, to see how far off we are. We just think, what's the biggest this can be, and what we're requiring, and let's say it's just 0.1. So we have 0.1. In fact, we just have 0.1 plus 0.1, so we really just have 0.2. Okay, that makes matters so much nicer. So we just have 0.2 raised to the third power, because 0.1 plus 0.1, right? Okay, and then we put that all over 3 factorial, and really that's the bound. That wasn't too bad in the end. In fact, you think, well, why didn't we just use this for single variable? Sure, but this example, though, at least illustrates how you could generalize that if you couldn't use a single variable Taylor series calculation, but still it was simple enough that we could easily come up with the result. And so this, let's just kind of remind ourselves. So this is how far off we are from the actual sum if we only use the or it's kind of an upper bound. So it's an upper bound for how far off we could be if we only use the first 2 terms of the Taylor series, or the, well, not first 2 terms, up to degree 2 in the Taylor series. Thanks for watching.